All right, let's just jump right in. Welcome to this explainer, where we're going to unpack the massive leap from building your standard basic AI scripts to engineering genuinely robust, production-ready cognitive agents. Today, we're pulling heavily from Chapter 10 of AI Agents in Action. That entire chapter is dedicated to exploring the cognitive agent, a system that actually thinks, monitors its own progress, and adapts on the fly. We're moving way beyond simple prompt chaining here, folks. This is really about architecting systems that don't just act blindly, but actively reflect on their own actions. We've got a ton of ground to cover today. We'll diagnose exactly why basic agents fail in production, define what cognition looks like in actual code, bridge psychological theories into software architecture, unpack the core blueprint, step inside the cognitive loop, and finally look at the emergent behaviors that come out of all of this. Section 1. Why basic agents fail. The painful reality of production deployments. Let's start with a reality check that is probably painfully relatable if you've ever pushed an AI agent out of a nice, safe sandbox and into the wild. In the lab, everything is perfect. The demo succeeds, you think you've nailed it. But the real world is just incredibly messy. So we have to ask ourselves, why does an agent that works flawlessly with standard tools suddenly completely lose its mind, hallucinate, contradict itself, or get stuck in an infinite loop when a user asks a slightly ambiguous question? The API tools were fine, right? The data retrieval was solid. The underlying model is state-of-the-art. So what went wrong? Well, when you ask a convoluted question that requires piecing together fragments of information from multiple sources or spotting contradictions, basic agents just fall apart. They end up stringing together a response that sounds super authoritative but is literally completely wrong. Here, we've mapped out exactly what goes wrong when these systems are pushed beyond their limits. You're probably going to recognize these 5 classic failure modes instantly. First up, the confident wrong answer. The agent pulls a document, blindly assumes it's gospel truth, and just regurgitates it without actually evaluating the evidence. Second, the broken record. We've all seen this. The agent endlessly retries the exact same failed API call over and over because it has absolutely zero stagnation awareness. It literally doesn't know it's stuck. Then there's the rigid plan. Say a user introduces new information that contradicts the original plan. A basic agent just ignores it and plows ahead anyway because it can't dynamically update its worldview. Fourth is the overcommitted guess. This is when an agent is asked about something it knows absolutely nothing about, but instead of saying, "I don't know," it confidently hallucinates an entire fabricated response. And finally, shallow composition. The agent knows how to use tool A, and it knows how to use tool B, but it completely fails to understand how to pipe the output of tool A into tool B. And listen, the fixes for these aren't just clever prompt tweaks. They require fundamental architectural changes. Section 2. Cognition and Metacognition defined. Moving beyond simple reasoning primitives. To fix those failures, we have to treat cognition and metacognition as concrete engineering concepts. And let's get our definitions straight first. When we say cognition here, we are not talking about AGI sentience or machine consciousness. It's much more practical. Cognition in software is simply the measurable quality of the agent's internal model of a task. A truly cognitive agent doesn't just read a prompt and spit out the first token that comes to mind. It builds a structured representation of the problem. It reasons about dependencies. And crucially, it dynamically revises its plan when new evidence comes in. It's all about breaking massive problems into chunks and constantly updating its understanding mid-flight. But here is where things get really interesting. Metacognition. If cognition is the quality of the thinking, metacognition is the agent's ability to think about its own thinking. Honestly, this is arguably the most critical capability for a production-grade system. Why? Because metacognition is your supervisory layer. It lets the agent structurally evaluate its own confidence, based on data points, not just the model saying, "I'm sure." It's what gives the agent that stagnation awareness we mentioned, acting as a circuit breaker to snap it out of a loop. And it provides knowledge boundary detection. A metacognitive agent knows what it doesn't know, allowing it to pause and step back instead of hallucinating. We really have to distinguish between standard approaches and true metacognition. Things like chain of thought or react, they're fantastic. They help the agent figure out exactly how to execute steps for a well-defined problem. But true metacognition acts as the boss. It's asking, wait, did we actually figure this out? And is it time to completely abandon this strategy and try something else? In the real enterprise world, where problems are ambiguous and data is contradictory, you absolutely need this metacognitive supervisor running the show. Section 3. 3 Theories of Mind, Bridging Psychology and Software Architecture. So how do we actually build this supervisor? Well, Chapter 10 borrows heavily from cognitive science. we're translating three famous psychological theories directly into our codebase. First, Marvin Minsky's 1986 Society of Mind. Minsky argued that intelligence isn't one giant brain process, but the emergent result of many simple, specialized parts interacting. We map this to specialized micro-agents, one for planning, one for execution, one for evaluation. None of them are a genius on their own. Second, Bernard Barr's global workspace theory. Barr's likened consciousness to a theater stage, where backstage processes broadcast their findings to a shared lit space. In code, this becomes our shared cognitive workspace, a central state that all our microagents constantly read from and write to. And finally, Daniel Kahneman's System 1 and System 2. System 1 is fast, automatic thinking. System 2 is slow, deliberate analysis. We implement this as an attention-based routing mechanism that dynamically shifts the processing depth based on how complex the user's query actually is. Section 4. Cognitive Agent Architecture Blueprint, the anatomy of a thinking system. Okay, let's take all of that theory and look at the actual engineering blueprint. This schematic right here is the holy grail of Chapter 10. You can see the flow. A user query comes in and cycles through these highly specialized modules. And notice how they all orbit that central hub, the global cognitive workspace. The query is perceived, memory is retrieved, attention routes the signal, planning picks a strategy, execution calls the tools, and evaluation rigorously checks the work. And every single step of the way, they are broadcasting their updates back to that central workspace. It is a continuous, living state loop. Let's quickly break down these 7 core components, because if you miss even one, the whole metacognitive illusion shatters. First, the cognitive workspace. In practice, this is a structured object holding task states and constantly shifting confidence scores. Second, the perception module. It just estimates complexity right at the start, so the system knows what it's dealing with. Third, the planning module. Instead of blindly executing, it selects a specific reasoning strategy based on the problem. Fourth is execution. This actually calls your external tools, often using Model Context Protocol or MCP servers. Fifth, evaluation. This is the internal critic, constantly looking for logic gaps in real time. Sixth, attention. This acts as the traffic cop, routing the workflow based on what's happening in the workspace. And seventh, memory. This builds a long-term knowledge graph of every success and failure the agent experiences. Again, remember Minsky's theory. None of these 7 modules are superintelligence on their own. The magic, the actual intelligence, emerges entirely from how they debate and share state in that cognitive workspace. Section 5. Inside the cognitive loop. Routing, iterating, and adapting in real time. If you ever find yourself debugging one of these agents, this routing tree is your best friend. This is Kahneman's theory brought to life in software. Look at the fast path. If the perception module says, hey, this is a super simple query, and memory instantly finds a successful past experience, the attention module just skips the heavy lifting. It routes straight to a direct response. That's System 1, fast, instinctive, and it saves you a massive amount of latency and tokens. But if the task is complex, or the evaluation module catches a contradiction, the system triggers the System 2 path. Attention explicitly routes control back to planning to test a new hypothesis, or to memory to find more context. The agent literally shifts its cognitive gears based on the friction it hits. Now we need to understand how nested this all is. The inner cognitive cycle we just talked about sits completely inside the outer agentic task loop. That outer L2 loop is managing the big picture, checking if the overall goal is done or if you're out of compute budget. But inside that loop, the inner cognitive cycle can spin multiple times in fractions of a second. The agent perceives, plans, executes a tool, evaluates the output, spots a flaw, routes back to planning, forms a completely new hypothesis, and tries a different tool, all before control ever returns to the outer loop. Just think about how powerful that is compared to a standard agent that just blindly runs a chain of prompts and hopes for the best. Within this loop, we have a non-negotiable safeguard, the confidence gate. Think of it like a strict bouncer at a club. Step 1. Evaluation updates the confidence score in the workspace. Step 2. The attention module checks that score. Step 3. If confidence is too low, you don't get in. The system is explicitly forbidden from responding to the user and gets sent back to gather more data. Step 4. Only if confidence is high enough does it pass the gate. This is absolutely crucial. It structurally prevents the agent from presenting a hallucination as a fact. And if it completely exhausts its budget without finding a confident answer, it gracefully degrades. It tells the user exactly what it tried, marks its uncertainty, and asks for help, rather than just taking a wild, overcommitted guess. Section 6. Emergent behaviors and metrics. The compounding returns of experience. When you wire all these modules together around that shared workspace and hook it up to a persistent knowledge graph, you get the real payoff: emergent behaviors. These are complex traits that nobody explicitly hard-coded, they just naturally arise from the architecture itself. Because the memory module is meticulously recording every win and loss in a knowledge graph, the agent develops curiosity. If confidence is low, it'll actually generate sub-goals to go explore adjacent topics, just to build context. It develops adaptive persistence. If a strategy fails, that failure is recorded. The next time it faces a similar task, it remembers the failure, avoids that path, and pivots immediately to a new strategy. It also learns selective depth, zooming through familiar problems using that fast system one path, saving tons of compute. And, of course, graceful degradation, knowing its own boundaries. By constantly recording its internal state, the agent's cognitive efficiency compounds, getting noticeably smarter and more adaptable with every single run. I want to leave you with a provocative thought here at the end. Right now, so much of the industry is obsessed with parameter count, just training bigger and bigger models to brute force baseline intelligence. But what if that's only half the puzzle? The cognitive architecture from Chapter 10 is completely domain agnostic. Whether you're debugging server logs, analyzing financial derivatives, or writing a novel, the global workspace and attention routing work exactly the same. So maybe the true path to artificial general intelligence isn't just about massive parametric scale. Maybe it's about building these modular, metacognitive architectures that finally allow systems to truly think, monitor their progress, and adapt to their own mistakes in real time. Thanks for joining this explainer. Until next time, keep building smarter.